Accumulators. I had the honour of meeting an engineer the other day who explained to me the function of accumulators. I hope I've got this right. Forgive me any errors, but I'll try and do this. Right, so basically an accumulator, cylinder containing a bag. Now when the cylinder is completely empty of water, the membrane inside will occupy the full volume of the cylinder. And as we push water in, the water will compress the air within the bladder and maintain equilibrium of pressure inside the bag against the water. So as the water pressure increases, so it causes the air to compress, and all the time the pressure will be equal in the air and in the water. So once we get up to the pressure of the standing pressure of the mains water coming in here, there'll be no further compression of the bag and the water will be stationary. Open a tap, the air pressure forces the water back out and will deliver the water at the standing pressure of the main, but on a declining pressure. So as the bag expands open, pressure drops and we'll get a sort of full pressure burst and a gradual drop off. But we could, for instance, have a standing pressure here that I'm going to use in my example of 4 bar, but actually have a very low dynamic pressure and a very low flow due to restricted pipework. This will actually overcome that incoming restricted pipework and allow us to size a pipework from the accumulator onwards down the pipeline, so we can get better flows and better use of our plumbing system in the house. This picture is just an example here of the bag being further deflated with more water in the vessel. So how do we work out this relationship? Well, what I had explained to me was Boyle's law. And Boyle's law is very, very simple. It is basically that pressure 1 times V1 equals P2 times V2. So just to work through an example, if we take a pre-charge in the membrane of 1.5 bar, multiply that by the volume of the vessel, and I've decided to go for a 200 litre vessel, we'll get a value of 300. Therefore, 300 will also equal P2 times V2. In my example, I want to use 4 bar, and that'll be times the volume 2. When we're looking at volume 2 here, we're talking about the air volume, not the water volume. Water can't be compressed. So if we then transpose that formula, we will get 300, which is our value we took from the first part of the calculation here. 1.5 times 200 equals 3. So we've got the 300, and we're going to divide it by 4. So just transposition of the formula. What we've done is divide this side by 4, divide that side by 4, these two cancel, leaving V2 this side. 300 divided by 4 equals V2. So if we do that sum, 300 divided by 4 equals 75 litres, which means in a 200 litre vessel we've now got the membrane only occupying 75 litres of the vessel, giving us 125 litres of water stored at 4 bar pressure. Now that could be quite useful. Now we can deliver that out to the system depending on our pipework size. The relationship that I've plotted seems to be linear. We start at 4 bar, dropping to 1.5 bar, with 125 litres down to 0 litres here. So actually when the membrane is completely filling the vessel, it will have ejected all the water, which is 125 litres, and it will drop from 4 to 1.5 following that line there. Now that might not be that useful. You don't want to be in a shower that's gradually getting lower and lower and lower. So what we use is a pressure reducing valve. I'll come back to my picture. Pressure reducing valve down line here, and I'm assuming a non-return valve back on the main here. I'm not sure about this, but this I am. So if I was to set this pressure reducing valve to 1.5 bar, for example, what it would do is it would actually supply a full 125 litres of water at 1.5 bar. Only once it got to 1.5 bar would we then go down to the normal incoming mains feed. Depending on the pressure in the main will actually contribute water to our system as well during this function, but I don't really understand the volumes of that and how it interrelates, so we'll leave that one. If we just assume we've got really, really bad water pressure, we would actually need to use a pump to fill the vessel, and we could fill it to 4 or 5 bar maybe, and then the pump would contribute its fill rate during the operation of the water system. So let's say it's giving 5 litres, we could probably add 5 litres a minute to the flow rate that we gain from this system. That must be it, a blank page. So just to recap, Boyle's law, P1 times V1 equals P2 times V2. Place in your pre-charge, your vessel volume to come up with the value. Take the value, divide it by your final pressure, your either pump pressure if you're filling it with a pump, or the standing pressure in the street, which will give you your new air volume. Take the original volume of the vessel, take off this reduced volume of air, giving you the storage capacity of the accumulator. From there you can work out how many vessels you need. So for instance, 125 litres could run 2 showers. Technically, if you were going to be 5-minute showers, you could, with a pump system, give you another 5 litres a minute. You could probably run 3 showers off of that. And you are allowed to pump off a main 12 litres a minute. So if you could add 12 litres a minute for the pump system from the main, I guess you could probably run nearly 4 showers off of that. So I hope that helps to explain it. Certainly did for me.